Dear students, in the last class we have discussed about the permutations and define the permutations composition of a under the composition of a functions. This permutation form a group X. We in the last lecture we have to just say that about the Sx form a group under the composition of a function. We have to really show that the composition of a 2 bijection is also a bijection. So far, for any f and g are the element of Sx, f composition g is also belongs to the S. So we can say that this Sx is closed under the composition of these two functions, and clearly also function compositions is associative. So for any f, g, h belongs to the X, so we can say that this clearly is equal to f composition g composition h is equal to f composition g composition h, and identity is clearly the identity function Ix which maps each element of x to itself is in x Sx and act as the identity element under the composition of that means for any f belong to Sx, f composition identity of x is equal to f, and the same as a f composition this satisfy this considered identity function is always is a bijective. So this function is work as a identity of under this composition of a function. And if we have a f is a bijective, then its inverse is also is a bijective. So if f is exists, then for each bijective function f belongs to Sx has an inverse, f inverse S is also belongs to the x, and f composition f inverse is equal to identity of x is the same as the f inverse composition f a. Now we have to move to our discussion for today's lecture is a symmetric group. The symmetric group is one of the most important examples of a finite group, and we will spend quite a bit of times investigating its properties. It will arise as a special case of the set Sx of bijection from a set X to itself. So let X if X is an infinite set, Sx is fairly hard to understand. One would have to be very either very brave or very crazy to try work with it. Things much more tactable and interesting when x is finite. So we just take a suppose x that x is finite with the n elements. That is, we can label the elements of x to be whatever we want, say numbers, pupils, flavored ice cream, etc. So we could simply assume that x is the set, x is equal to, we write into the 1, 2, 3 and in this form. So we just define this symmetric group, means let x is equal to 1, 2 up to n, where n is greater than or equal to 1, and let Sn be the set of all permutations of a x. The group S under the Sn composition of functions is called as a symmetric group of n letters of x and denoted by Sn. So we just take a mapping, an element of Sn is a bijection from f1 to n2, f1 and so on to n, and it is simpler terms it rearrange the numbers 1, 2, 3 we can represent a bijection of a pi of 1, 2, 3. We have to take a simply n is equal to 3, and we define the bijection is the form of pi 1 is equal to 2, pi 2 is equal to 1 and pi 3 is equal to 3. With the following diagram, pi we have to map is a pi, and 1 goes to 2, 2 goes to 1 and 3 goes to 3, and in the two row notations of the symmetric group, we can say that 1, 2, 3, 1 goes to 2, 2 goes to 1 and 3 goes to 3. Later on also we have to say about this example. So, we just first we have to just try what is the order of a symmetric group Sn. So, the order of a symmetric group Sn is factorial n. So, now we have to prove this how many permutations exist for the set 1 to n. To define a permutation pi on 1 to n, we need to specify where each element is mapped. For example, we just say that for pi 1 there are n possibilities. So, we have a pi 1, we have to n possibilities. So, this is pi 1 is equal to, we have a possibilities 1, pi 1 is equal to, we have possibility 2, and then we have a pi 3 is equal to also pi 1 is equal to 3, and so on. We have a pi 1 is equal to n is there. So, we have a for pi 1 there are the n possible choices. We have a pi 1 is equal to 1, pi 1 is equal to 2, 3, and so on. So, we have a total, because there is a n letters. So, we have a total is the n choices for a pi 1. Now, for the next pi 2, that means one choice is we have to also is remove. So, pi 2, since pi 1 is already is choosing. So, this means if is choosing, then we have a, and the set is a n minus 1 elements are left. So, then we have a phi 2, we have to just there are only n minus 1 remaining options is there. So, for pi 1 we have n choices, pi 2 we have n minus 1 choices, and if we go to the pi 3, then pi 3 is we have a n already 1, pi 1 and pi 2 is choices already chosen. So, we have a total possibility choices are n minus 2 choices for pi 3, and in the similar fashion pi 3 is n minus 2 choices are available, and this process is continue. So, we have to pi 4 is equal to, we have a n minus 3 choices, because n minus 1 and n minus 1 and minus 2 is already chosen. So, we have a n minus 3 choices left for pi 3, and in the finally for pi n only one choice is remain. So, if we have a pi n minus 1, we have a 2 choices, and pi n is we have only one choice is remains. There are the total number of permutations of 1 to n is for pi 1 is equal to n choices. This is for pi 1, pi 2 we have a n minus 2, pi 3, and then so this is a pi of n minus 1, and this is a pi n 1. So, these are the total choices are there. So, this is n minus 1, n minus 2, and so on up to go to 2 into 1. So, we can say that simply this is equal to factorial n, hence the number of possibility choices Sn is equal to we have a factorial n. For example, we have a we just say that S3. So, S3 we have a this means clearly the order of this S3 we have a factorial 3. That means we have a 6 possibilities are there. There is a 6 members of in the group of a S3. Similarly, if you take a S4, then you have a factorial 4, and then you have a similarly we have a 16 elements in this form. So, factorial 4 elements are into this form. So, we have to just say that so, in this factorial 4, now one of the nice things about working with the permutation of a finite set is that we can completely describe what they do. That is, we can write down a table that completely describe a given permutation. For example, suppose we have a pi belongs to the S3 is given by the picture. We have to just say that in previously we have to define into this form. We have a picture like this. We have said that 1, 2, 3, 1, 2, 3, and this is a map is a pi, and we have said that pi is 1 is equal to 2, and then is equal to 3 is this. So, pi 1 is equal to 2, pi 2 is equal to 1, pi 3 is equal to this bijection map is defined to form. This is clearly. So, this is the map we have to define in this form 1, 2 and so on. Of course, we are going to represent permutation in this way. It would be help to know how to multiplication works in this notation. So, theta, for example, let theta is equal to, we have a 1 to 3 pi 1 goes to theta 1 is we have a clearly theta 1 is equal to 2, we have a theta 2 is equal to 3 and theta 3 is equal to we have a 1 in this case. Similarly, with the remember the multiplication we have a purely just composition. So, pi we have a this is pi of this, then this is theta of this, then we have to composition of these two 1 2 3, then we have to pi times theta of 1, then pi of theta 2 and 3, pi of theta 1 is equal to you have a 2, pi of theta 2 is equal to you have a 3 and pi theta 3 is equal to you have a 1, and then we have a composition of pi and theta is equal to we have a 1 3 2 in this form. Then on the other hand theta phi is a similar fashions, we have to write this 1 2 and 2 3, so 1 3, and then similar fashion we have to write the other elements of this. So, 2 goes to 1 and then 1 goes to 2, we have a 2, 3 goes to 3, 3 goes to 1, then 1 goes to we have a 3 goes to 1 is this. Yeah, we have to just write into this. So, we just write as a in the form of this complete table is coming to this 1 3 2 1 1 2 3 3 3 1, and then we have to write the theta of phi into this form. In other words, we computing the product of a two permutations, we move from right to left. First locate the number below 1 in the rightmost permutation, then find the same number in the top row of the left permutation, and finally write down the number directly below it. Repeat this process to the rest of integer 2 through n. So, for example, above we have to note that theta, pi theta and theta pi are not the same. What does this tell us? We have verified that S3 is clearly is a non-abelian, and this result is hold generally. So, we can generally prove this result, and we show that Sn is clearly is non-abelian. This is the Sn is a non-abelian group is there. For n is equal to n greater than equal to 3, Sn is a non-abelian group. So, we have to just take let theta, pi and theta are the element of a S3 be defined as in example. So, we have to just we have to define in the example, and simply pi of 1 is equal to we have a 2, pi of 2 is equal to we have a 1, and pi of 3 is equal to we have a 3, and you see clearly we have to define is a theta is equal to theta 1 is equal to 2. So, we have a we define into a this form theta of 2 is equal to theta of 1 is equal to 2, theta of 2 is equal to 3, and theta of 3 is equal to we have defined into a 1 form. And you see this clearly we have to show that this if this this clearly we have to previous example we show that theta pi theta is not equal to theta into pi. Here you can just see this is theta of pi is in this matrix, and now you can see this is equal to 1 3 1 goes to 1, then you have a pi of theta, we can say some pi of pi theta 1 is equal to 1, pi theta 2 is equal to 3, and we have a pi theta 3 is equal to 2. But here we have to just see theta pi 1 is equal to 3, theta pi 2 is equal to 2, theta pi 3 is equal to we have a 1. So, theta pi 1 3, but here we have a 1, then you have a clearly this is a 3 and this is not equal to, we have a pi theta 1 is equal to, we have a 1 here. Okay. So, similarly other, this is clearly not equal to pi theta 2, that is equal to sorry, this is pi of is equal to 3 and this is not equal to pi theta 3 is equal to 2 is there. So, for S3 clearly this we can show that this theta and pi is the element of S3 and we define this example. So, S3 is a non-abelian. Now, we have to this n for n greater is equal to 3, this is done by this previous example. Now, we have to suppose n is strictly greater than 3, then we define it to by bijective function pi bar and theta bar of Sn is pi bar I is equal to pi of I if I lies between 1 to 3 and I if I is strictly greater than 3. Like this, we have to pi bar is equal to 1 pi 1 pi 1 and now you just say that it's pi of 1 we have a 2, pi of 2 is equal to 1 and pi of 3 is equal to 3. We define in the this example this form. So, we say that pi bar of I is equal to pi of I. So, this is pi of I means pi of 1, pi of 1 is equal to you have a 2, then 2 this is 2, then this is you have a 1 and this is equal to 3. He says that if I is greater than 3 then you take a I. So, if as a pi is equal to 4 we have a 4, 5 is equal to 5 and so on, n is equal to pi pi of n is equal to n is there. So, simply we have to define pi bar is into this form and also theta bar is also the similar form. We have to theta bar I is equal to theta I if I lies between 1 and 3 and I if I is greater than 3. Here also we have to define is theta 1 is equal to 2, theta 2 is equal to 3, theta 3 is equal to 1. So, now we have a 2, 3, 1 is this is defined by theta I and rest of them elements is a 4 and so on are the same we have to write it. So, we have the theta bar and pi bar belong to the Sn. Now, we are calculating the pi bar and theta bar is clearly into this form 1 3 2 we have to already calculating into this form, rest of them is equal to similar where 4 to n this is the identity, 4 goes to 4, 3 goes to 3 and so on. So, we have a like this pi and theta conjugate 4 is equal to 4, pi bar theta bar 5 is equal to 5 and so on, pi bar theta bar n is equal to n in this form. So, 4 to n is the identity we have to just say. Similarly, we have to calculating the theta bar pi, you can just see this is already we have to calculating for in the case of S3 and again we have to taking for by 4 to n we have to again identity. Now, this is if we take a 1 3 2 the 3 2 1 and then the rest of them is the same. So, we clearly show that this show that pi bar and theta bar is not equal to theta bar pi bar. So, we can say that Sn is a non-abelian group for all n greater than equal strictly greater than or greater than equal to 3. Now, we have to already show that equal to 3 is already is a non-abelian and then if we take n is strictly greater than 3. So, also we show that the result is hold for if you define and map into a this form clearly. So, this shows that Sn is a non-abelian group for all n greater than equal to 3. Now, we have to define the next is the inverse permutation. For any permutation pi, the unique permutation theta such that theta pi theta is equal to identity permutation or we have to theta pi is called the inverse of a pi and it is denoted by pi inverse. For any permutation pi, the unique permutation theta such that a unique permutation theta is exist, then we can say that if theta pi is equal to identity and pi theta is also identity, so we call that this means inverse of a pi, and it is denoted by pi inverse. For example, let's this pi is equal to, we have a this element. So we have to 1, 2, 3, 4 and so on. The inverse of a pi can be obtained reading the array from bottom row to the top. So we have simply like this, we have to take bottom row to right. So we have a 2 means like we have to write into this form. First we write in the form of 1, 2, 3, 4, 5, and then we read this is, we have to just write as the pi inverse. So pi inverse into this, we read this table into the bottom to the up. So 1 to 2, so this is 2, then 2 to 3 we have to write as a 3, then 3 to 1 we can write 1, 4 to 5, and then we have 5 to 4 is like this. So the inverse of a pi can be obtained. That means we have to such a matrix is exists this into this. If you take a composition of these two, we getting clearly identity element. You just verify this 1, 2, 3, 4, 5. Now we have a 3, 1, 2, 5, 4, and then we have to taking this matrix 1, 2, 3, 4, 5, and then this is equal to 2, 3, 1, 5, 4. Now we have a 1, 2, 3, 4, 5, 1, 2, 2 to 1, and now we have a 2 to 3, and then 3 to 2, 3 to 1, and 1 to 3. Now we have a 4 to 5, 5 to 4, and we have a 5 to 4 and 4 to 5 is there. So this is clearly we have a identity matrix is there. So this is a identity permutation. So we can say that if we take this means we have a any permutations is given, then we can read out the inverse of this permutation directly from this way, reading array from bottom to the top row. We can write the inverse of a such a into this. This I already explained you this example. That one is in the bottom row must be mapped to the number above it is, which is 2. So 1, 2, 2. Similarly, the others I already explain you into a this form. We can write the inverse of any permutations easily. We write a inverse. Let theta is equal to this, then we have to try to find out the what is the theta inverse. So we can just read out the theta inverse. Theta inverse we can just say that 1, 2, 3, 4. Then this is 4 to 1 is equal to 3. Then we have a 2 to read as a 4. Then we have a 3, we have a 1. Then 4 we have to read out as a 2. So this is clearly theta inverse is equal to, we have a 1, 2, 3, 4, and then we have a 2, 3, 4, 2, 1, 2 the inverse of a this clearly is just. So theta if you take theta 4, 1, 2, now you see this is this clearly, this means this is the same mapping is here, then these two are the same. That means we can say that simply is a theta is a it's a self inverse. So this means now theta is itself, so theta is itself on inverse. Now it would be entirely feasible to compute the group table of for Sn at least relatively small n. So we just start for a symmetric group of order 6, 3. So let x is equal to, we have a 3 element. The possibility permutation can be written in the form identity permutation is clearly, we have to just say that 1 goes to 1, E1 to E2 and so on, IA, and then we have to just say that equal to 3. Identity permutation is 1, 2, 3, 1, 2, 3. and rho is equal to, we have 1 2 3, 1 is 2 3 and 1, and then pi is equal to 1 2 3, that is equal to 2 1 and 3. Then we have a pi, then gamma is equal to 1 2 3, then you have a 3 2 1, and then we have a delta is equal to 1 2 3, then delta is equal to 1 3 2, and then you have a eta is equal to, we have a 1 2 3 3 1 2. This is correct. This is written all the table. This is a, I just mentioned, this is a correctly this table we have to write in this form. So this is, I just mentioned into this form. I just E1 E identity, rho and zeta, delta, gamma and pi in this form. We have to in this we have a fixing this 2, and then we have to rotating by 3 and 2, and I explain you this in details about the how to be this constructed as a table this permutation by using the d-Hydels group of order 3. So we just write into this form. Now this S3R is equal to, this is a the Keeler table of S3 we can compose in this form. Now we have to take a composition of identity, and identity is equal to identity. Now identity of rho is clearly rho, and then this is not a problem. We have to take a composition of a rho and a rho, and then you have a rho is equal to, you have a sorry, rho is equal to, you have a 2 3 1. So we can just say that 1 2 3 2 3 1, that is equal to rho. Now we take a composition of a rho with composition of rho. So rho composition rho is equal to 1 2 3 2 3 1 1 2 3 2 3 1. Now this is equal to 1 2 3 1 2 and 2 is equal to 3, 2 goes to 3, 3 goes to 1, 3 goes to 1, and 1 goes to 2, and then you can see this is equal to, this is the same as a zeta. You can just see 3 1 2 in the bottom, this is equal to this is 3 1 2, and this is giving the composition of this rho into rho square is equal to into this form. Similarly, you have to just rho and zeta is equal to identity. Rho is equal to, you have a 1 2 3 2 3 1, and then we have to take a zeta is equal to, you have a 1 2 3 3 1 2, and this is giving you a 1 2 3 3, and 3 goes to 1, 2 goes to 1, 1 goes to 2, 3 goes to 2, and 2 goes to 3, and this is equal to identity. Yeah, we can say that identity. So clearly this is giving you identity. Similarly, you have a zeta into zeta square is giving you have a rho. So we have to just verify this one also, and then leave rest of them. We can just 1 2 3, then 3 1 2, and then 1 2 3 3 1 2, and now we can say that 1 2 3, 1 goes to 3, 3 goes to 2, 2 goes to 1, 1 goes to 3, 3 goes to 2, and 2 goes to 1. That is the same as a rho. Similarly, all other we can just say that pi is a square is equal to identity, gamma square is equal to identity, delta square is equal to identity. So clearly gamma and pi, gamma, delta and identity are the self inverse, but rho is the inverse of a zeta, and zeta is a rho inverse of a rho is there. So just we can say that these two are the inverse each other, and the rest of them is a inverse of a self inverse is there. So we have a pi is a self inverse, and then we have to just say that the following tables gives the inverse of the permutation. This identity, inverse of identity is equal to itself. Then we take this is delta, delta inverse is also because is giving identity itself. So this is also because delta square is equal to is giving you a identity. And then we have a gamma, gamma is also is a self inverse, so gamma square is also giving the identity. Pi is also self inverse, so pi square is also giving you a identity element. Then rho square is equal to giving you a inverse of a rho is equal to zeta, and but rho to the power 3 is giving you a identity. Similarly, zeta inverse of a zeta is equal to, you have a rho, because we have a this two rho and zeta is giving you the identity, and we have also zeta and rho is also giving the identity. So, this means rho and zeta are inverse to each other, and this power 3 is equal to identity, power 3 is equal to identity, and the rest of them is equal to, you have a, they are the self inverse. So, it means is clearly we have to say that that inverse square is also the inverse into this thing. So, this is clearly we have to discuss the Cayley tables of this S3, and then easily we can show that, that means all the elements of this tables are the. So, this is a clearly is a form a group, and this is clearly is a non-abelian group, because if you take the pi composition zeta is equal to, you have a gamma, and you have a zeta composition pi is giving you have a delta. So, this means clearly these two are not the same. So, this is clearly we can say that this S3 is form a group, and also the inverse we can find that inverse of all the elements are itself except rho and zeta. In rho, inverse of a rho is equal to zeta, and the inverse of a zeta is equal to rho. So, this is clearly the we have to discuss details about this S3 is a group under the this composition of a permutation. Now, I have to stop today's lecture here, and in the next lecture we have to continue the order of a permutations and some other properties of a this symmetric groups we have to continue into the next class. Thank you for today.